All right, well, good afternoon, grade 12s. I am excited today, because it's so exciting to tell you about this, one of the most famous experiments in physics. Okay, this is the famous Thomas Young's, I'm sure you've heard of it, okay? Thomas Young's double-slit experiment. Now, if you just Google it, it's just all over Google, guys. This is a big social media sensation. Okay, Thomas Young's double-slit experiment. What it did was, for the first time ever, back in the mid-1800s that is, the first time ever, it showed that light produces interference. Okay. Now, I'm just going to get right into it. So I've set up a couple of demos. I hope this works for me here the way I'd like it to, so we'll see. But anyway, here's the deal. So number one, I showed you yesterday that when you have two slits and waves hit those two slits simultaneously, then what happens is you get an interference pattern. So I'm just going to show you this. So let's go here. I will run the waves. So here come the waves. Okay. They're going to hit the two slits that you see right here. So here's my three walls. Okay, and there's two openings. Okay, and then what happens is here they behave like two sources. And if we look at the 3D view, we clearly see that interference pattern forming with the nodal lines and antinodal lines here, the faded out nodal lines and the bright antinodal lines in between. All right, I'm going to stop that there. So here we can clearly see that interference pattern. Okay, good so far, right? All right, but here's the thing. If you take a flashlight, let's say, and you shine it on two slits, you're going to find that, like, let's say you put two little pinholes in a piece of paper or something, shine a flashlight on it, then you look at the light hitting the wall on the other side. You're not going to see any interference. Okay, and that was Huygens' problem in the late 1600s. Okay, he wasn't able to demonstrate that light produced this kind of interference. So if you just try this with an ordinary light source, it doesn't work. Okay. And what light sources did they have back then? Well, they had candlelight, they had lanterns, they had lenses, they could focus the light into a beam, that was no problem. But, that's what they had, right? So they had these kind of light sources, they tried the experiment, didn't work. You had two candles side by side, that doesn't behave like two sources, and you don't see any evidence of interference, right? So you go to church and you see all the candles side by side, let's say, where you're, offering up prayers for people and stuff like that, you will not see interference of those candles anywhere. Okay, like you don't see it with your eyes, you don't see it on the wall, nothing like that. You just see like a bunch of candles, like the light overlaps on the wall, but no interference pattern, like no bright and dark spots, let's say, okay, that looks anything like this. So what's wrong? Why doesn't it work? Well, it has to do with how the light sources themselves work. Okay, so here's the deal. When a candle or a flashlight or any ordinary light source, a light bulb of any kind, when it emits light, see, how does it emit light? Like what's going on inside it to emit light? And there's, various forms of luminescence, okay? But generally speaking, light bulbs, especially back in the 1800s, work by incandescence, which means you heat something, whether it's a filament in a wire if you have an electric light bulb, or just a candle, like you heat up the wick with the flame, and it gets hot enough, it glows, okay? But here's the thing, the wick is made of atoms, okay? A filament in a light bulb is also made of atoms. In a fluorescent light, the gas inside the fluorescent light bulb is made up of atoms. Everything's made up of atoms, right? Now, Huygens didn't know about atoms. Thomas Young even didn't know about atoms. There was a theory that said that maybe like everything is made up of these indivisible atoms, okay? But they really had no idea what the structure of these atoms are. But everyone knew that light comes from matter, right? Like it doesn't come from nowhere, it just doesn't appear out of thin air. It comes from somewhere, it comes specifically from atoms, okay? And atoms do something to emit light, okay? And what are they doing? Well, it turns out, okay, that what they're doing is they're kind of stimulated by the heat. And when they're stimulated, it's almost like a kid jumping up and down in the water. Okay, so picture like 6 kids in the water. Okay, so these dots here represent 6 children in the water. You're going to throw them each a candy. And when they get the candy, they jump in the air. Okay? Now, that'll produce a wave in the water when they jump up and down. Now, that is kind of loosely what happens with atoms, right? You stimulate them with heat, they get energy, they kind of jump up and down, and they produce light. That was the theory. Okay? Now, if they're all jumping up and down at exactly the same moment, then we get a coherent wave in the pool. But if you've ever been to a pool where there's families playing in the water, you see waves for sure, but they're not all doing the same thing at the same time. And so there's no pattern to the waves. It's just a random jumble of waves. Okay? So what I've done is I've set up these sources to do exactly that. They're going to jump up and down at different frequencies and at different times. Okay? Like 6 kids playing in the water, right? You're throwing them food, whatever. They're jumping up and down for joy because you're throwing them candy. Okay, maybe you shouldn't be swimming and eating at the same time, but whatever, that's what they're doing. And they're producing these waves. Now, I have my double slits down here, okay, but watch what happens this time. It's very different. Okay, now I'm going to increase the resolution, and I'm also going to slow it down. All right, so let's see what happens. So here we can see they're jumping up and down at random times. Okay, and we get a really sort of odd swirl of waves here. Now, even if I change the frequency of these sources, they all have their own frequency. But if you look down here at the bottom, okay, we'll look in the 3D view, we're not seeing any nodes and antinodes here. Okay, why not? Is the question. Why don't we see any nodes and antinodes with this weird? Here you can see the kids jumping up and down over here at the top. Why don't we see the nodes and antinodes? Well, if you think about it, let's go back to our 2-dimensional view. If you think about it, okay, and I'm going to stop when we clear these waves, and I am going to start it again, okay, and so you see what happens. Okay, so let's start it again, and then I'm going to pause right here. Now, if you look what's about to happen, a wave is about to pass through this hole right here, but it's going to not pass through this other hole at the same time, okay? And so the two holes will diffract the waves at different times. And so we're not going to get, like, in order to produce two-source interference, you need to have the two sources in phase. That means they're producing waves at the same time and the same frequency. Well, the problem with this jumble of waves that's occurring here is that waves will arrive at each slit at a random time. And so because it's not arriving at the same time, we won't see any interference. And that's the problem with ordinary light sources. So these kids jumping up in the water, that's like how every light source in nature really works. Okay, whether it's a natural occurring thing like chemiluminescence or bioluminescence in an insect, or the sun, or a candle, or a fire, or a light bulb, whatever the case may be, most light sources, artificial and otherwise, produce incoherent light. In other words, the atoms are releasing the waves at random time intervals. And when those waves hit these slits, there's just no way for it to produce any interference. Okay, so we'll let it go. And you can see what's happening here is there's just random times in between these waves. There's no pattern to it. Well, there is probably a pattern to it, but there's no interference pattern because it's too chaotic. Okay, so here in the 3D view, there are no lines forming of interference that anyone can see. Okay, and without any lines of interference, there's no interference pattern to observe. Okay, so that's a problem for Huygens, right? He tried this experiment with whatever light source he had. It didn't work. And that was considered a huge weakness of Huygens' theory, okay? Now, Thomas Young comes along, and he doesn't have light sources 200 years later that are any better than Christian Huygens. But he realized that this was the problem, and there's a way to fix it, okay? So his eureka moment was to do this. Okay, so here we have our 6 kids in the water, but this time we've added something else. We've added another slit. So there's a single slit right here, okay? And then over here you have your double slit apparatus. So what he did was he placed a single slit in front of the double slit because he knew okay, that what was happening, the problem, why we couldn't see any interference was that the waves are reaching the two slits at different times, and therefore we're not getting a stable wave pattern to produce a stable interference pattern, okay? So to fix it, you put the single slit here. Now that single slit will diffract the waves from these kids splashing in the water, and those waves from this hole will hit these two slits at the same time. Now, watch what happens. So here we go. I'm going to let it go. Okay, I'm going to slow it down. Sorry, it's a little laggy. All right, so now look. What's happening is the waves from the kids hit the first slit, and then those waves from the first slit diffract and hit the second slit at the same time. And if you look here, we can see a pattern forming. Okay, so let's look at the 3D view. And, sorry, I've got it turned around. Here you can, let's see if I can, you can clearly see our lines of interference forming, nodes and antinodes. Isn't that amazing? Okay, so what a stroke of genius. Like, he realized before anyone else why those ordinary light sources just don't work. Okay, they don't work because the waves are incoherent. So light sources that produce incoherent light, in other words, where all the atoms are just individually jumping up like kids splashing in the water at random times, that chaotic wave pattern can never produce a stable interference pattern. But if you put a single slit in front of the double slit, that will produce waves that are in phase that strike the second pair of slits at the same time. And here we go, we get the interference. And so when he did this experiment, it was considered a massive thing because up to that point, they were still teaching Newton's theory in school that light was a particle, okay, in universities and stuff like that. So this changed everything because as soon as Thomas Young was able to do this experiment and show that light produces interference, well, case closed. Only waves can do that, okay? And so this was considered a really sort of ground, earth-shattering, at least in scientific terms, experiment. Like it just rocked the scientific community because, you know, when you're teaching Newton's theory, which, to be fair, they had no evidence that Newton's theory was correct. It's just he was considered, they just favored Newton because he was the more famous scientist. Unfortunately, not the way science is supposed to work. But that's what happened. But then Thomas Young comes along, does the experiment, shows that light produces interference, and boom, there you go. Now, I'm going to point out one more thing to you. So I'm just going to stop this one. So here we clearly see the lines of interference that we expect. Antinode, node, antinode, node, right? And such a brilliant, let's go back to the two-dimensional view, such a brilliant thing to do. So these waves are out of phase here, but they strike the single slit and then the double slit simultaneously. So that's really brilliant. And here you can sort of see the nodal lines here forming down there. All right, now before we leave our simulation here, I just want to go back to this one here. So let's go back to this. Let's go back to, I'm just going to clear it. We don't need to do in the modern world in 2020, we don't have to do Thomas Young's trick with a single and double slit, okay? We don't have to do that to make the experiment work because we have a source of light that is a modern invention invented in the last 100 years, okay, in the mid 20th century or mid 1900s if you like. So that experiment, or sorry, that device is a laser, okay? So laser stands for light amplification by stimulated emission of radiation. It's an acronym, right? So that's what a laser is. And lasers, all the atoms in a laser, so like imagine you get your kids in the pool and you say, okay kids, we're going to be like a laser, okay? So in a laser, all the atoms are jumping up and down at exactly the same time and exactly the same frequency, okay? And the waves that come out of a laser are all in phase, right? They're all in step. So if we just take a laser beam and we shine it on a double slit, we don't need the single slit in front of it because those waves are going to hit the two slits at the same time and you get a very dramatic interference pattern, okay? Like it's very clear that we're seeing interference of waves just like you would expect. So in other words, laser light produces waves that are exactly like this, okay? So they produce basically plane waves, you know, like in other words, one wave after the other, all in a row, okay? And when those hit the slits, as you know, when those hit the slits, you're going to see interference. Here we can see the lines forming very clearly, okay? So we can simulate that in a ripple tank, no problem. Here we can see our lines. So this is how lasers work. They produce coherent light. In fact, they're the only light source we have that does that, okay? So anyway, that's it for the demonstrations. I know it took about 15 minutes to go through those things, but Thomas Young's experiment, so cool, okay? And such a simple fix, right? Putting the single slit in front of the double slit. But now the next thing for us is we're going to do the experiment with the laser, and then I'm going to show you how you can use the laser to do one of two things. Number one, we could, for the first time, let's say, for us, measure the wavelength of a light wave. You know, exactly what is this wavelength? How do we know what the wavelength, like, for example, I know that red light has a red laser has a wavelength around 630 nanometers. Well, how do I know that? Okay, I can't see the waves, but this experiment will tell me, okay? And of course, that obviously proves it's a wave, right? If I can measure its wavelength. The other thing is you can measure something really small with these experiments. So if I have two atoms, or like, you know, not two atoms, let's say two tiny holes in a sheet of paper, and those two holes are extremely close together, like let's say they're only a hair width apart, right? Like a few microns apart. Well, if I shine the laser through it and the waves diffract, I can use the interference pattern to determine the distance between the centers of those two holes, and therefore measure the width of that hair down to an extreme level of precision. And in fact, that's exactly how we measured small distances. We use laser light to do it using, we call it laser diffraction experiments. Okay, if we want to measure the distance between atoms, we need to use really short wavelengths, so we call those X-ray diffraction experiments, where we use like a laser that produces X-rays. Okay, and then we beam that at the two slits, and of course we need like to develop some film or whatever to see the resulting interference pattern. But you can measure things that are incredibly close together, like the distance between two atoms. So it's really quite amazing. Okay, in fact, we've used those kind of experiments to determine how crystal structures are made in like fine crystals. In other words, where are the atoms in these really small crystals? Well, X-ray diffraction will tell us. It'll tell us the distances between the atoms, and we can work out the geometry from there. This is really cool. Okay, and when Thomas Young did this, at the time, the big news about it was it disproved Newton's theory. Okay, but since then, we've found a whole bunch of things that you can do with light as a result of this. Okay, and with the invention of the laser, it's really exploded our knowledge. Okay, as a result. All right, so we'll stop there for now, and I'm going to continue this in the notes.